So as some of you know, I am doing two different things in research, symbolic dynamics and also quantum computing. And this talk is part of a program of using ideas from quantum computing to do things in symbolic dynamics. So you will see a lot of categories, but you will see them. You will not, there will not be text, there will be pictures. So essentially, the goal is to try to understand better one of the main open questions in symbolic dynamics, which is topological conjugacy in 1D. So first, I will explain quite briefly the point of view I take about this problem. So again, the objective is to try to find new methods to investigate the conjugacy problem for shifts of finite type in 1D. And of course, in 1D, there are many different representations, and the one that will be good for the talk is using matrices. So as you may know, in dimension 1, the most important shifts of finite type are the edge shifts that are the set of B-infinite walks in some graph. And this graph is entirely characterized by its matrix. And instead of trying to understand the conjugacy problem on the graph, you can try to understand it on the matrix. So conjugacy problem is to know if the set of B-infinite walks are isomorphic up to some cellular automata. And you can rephrase it in terms of graph, in terms of matrices. And this is how you do it. So first, you do it from one step, and then the equivalence is n steps of this. So one step, you say that two matrices M and M are one step equivalent if one is RS and the other is SR for two matrices SR that are non-negative. So that's the important part. So for instance, these two matrices M and N are one step equivalent because M is RS and N is SR for the two matrices below. So this is what is called one step equivalent, and then if you take the transitive closure of that, you obtain something which is called SSE equivalence. And this is exactly the same as conjugacy. So this is a way to see conjugacy in terms of matrices. So you have this operation of matrices, and that you say that RS is equivalent to SR. And you can do this many steps. And you want to understand what you obtain. What is this object? What is this equivalence on matrices? So for me, I consider it to be the main open problem in symbolic dynamics to decide conjugacy of shifts of finite type or SSE of matrices, which is the same problem differently. So this has been open since the 70s. And there are some cases that are decidable. So for instance, if the matrices are in Z, so you can have negative coefficients, then it is decidable. And if you look at one-sided edge shifts, then it's also decidable because it's similar to, because you can transform the problem in a rewriting problem for graph, and then the system is confluent, which means there is a way to always simplify your graph. So this doesn't work for the problem that I'm interested in, so two-sided edge shift in N. So non-negative matrices and this equivalence. And so I will try to use some techniques that are coming from category theory to investigate it, and to see if we can come either to new results or to better understanding of some existing results. So to do that, what I will do today is try to present in something that might be new for a lot of people in this room, how to represent matrices in terms of pictures using some kind of generators and relations. And once I have done that, we will see how I can use this representation of matrices to change the problem into a problem of pictures and equivalence of two pictures, and how I can use that to obtain invariants, so conjugacy invariants. So the first part of the talk will be mainly about how to represent graphically matrices, so how to represent matrices with generators and relations. So I will give directly what are the relators, the generators, and then I will explain how we come to these generators. So it turns out that you can represent any matrix starting from just 6 matrices, this one, and using 2 different laws. So the first law is obviously the composition of matrix, multiplication of 2 matrices, and the other law is the sum of matrix which means that you take the diagonal A, B. So if you take these 6 generators and the two sort of composition laws, so the multiplication and the sum here, you can represent any non-negative matrix with that. So just to be clear, there is something which is slightly strange, is that, of course, I am dealing with matrices with n rows and m columns, but n and m might be 0. Okay, so and that's why you have the 2 last matrix, which are a 2 by 0 matrix and a 0 by 2 matrix. But this is the last slide where I will speak about these 2 things. They should be present in all the remaining slides for it to be clear and precise, but it's always a bit weird to think about matrix with 0 rows, so I will not speak of them. Okay, so what are the other 2? So the first one is just the 1-1 matrix with a 1, and then you have the 1-2 matrix with 2 1s, the 2-1 matrix with 2 1s, and the 0-1-1-0 matrix, which you can understand as a permutation of the 2 rows and the 2 columns. And this is quite obvious, because, for instance, if you take the matrix 1, 3, 2, 0, then you can write it like that. Okay. And now we need to understand what I have written here, and why it is quite obvious that 1, 3, 2, 0 can be written like that. And that's the rest of the talk, essentially, of this part, to try to understand this. So you see that I used 1, 1, I used 1, I used 1, 1 in the other direction. I cheated a bit in the middle, because this is a matrix of permutation, but if you can do a 2 by 2 matrix of a 2 by 2 permutation, and you can use the sum, it's easy to see that you can do all permutations, so that's why I use this one instead of a different representation. But now I want to understand that, and the point of view I will take is to use pictures. So we'll forget about matrix for a while with this formalism and use a formalism with pictures. So this is what a matrix here is now. Matrix is just something with some wires, input wires, output wires. And if you want to understand what the matrix does, well, you take as an input a vector v, and you look at what is m of v. That's what we are doing. So we'll represent matrices with boxes, with some inputs and some outputs. And now we will see what the 4 generators look like in this context, and what the 2 composition laws look like in this context. So first, it's quite obvious that the 1-by-1 matrix just takes a vector v and sends it to the same vector v. So it's just a wire where nothing happens. I will not put a m inside because nothing happens, it's just a wire. So 0, 1, 1, 0, it's just a crossing of wires. So again, I will not put a m everywhere to put it, we'll just put 2 wires and I will cross them. Before looking at the other 2, let's look at the 2 composition laws. So what is m times n? Well, it means that you first apply n to your vector, then m, which means that graphically you will represent it like this. Okay, nothing special. But actually there is something happening. Is that if I want to do pictures, it should be true that anything that is true of pictures should be true of the composition law itself. So for instance, for pictures, it is quite clear that if I do A, then B, then C, the order is not important. I have associativity. So it should be true of the law, otherwise I could not do any picture. For the picture to make sense, the law should be associative. Okay, so this is m times n. And now if I look at m plus n, so if I take a vector v and I think of v as having 2 parts, u and w, then it's clear that m is acting on u and n is acting on w, which means that the good representation of this is to just put them in parallel. Okay, so the sum, the Kronecker sum of 2 matrices is just putting the 2 matrices side by side. And again, for this to work, it should be clear, it should be true that the law that I'm taking is associative, for the same reason as what I previously. Okay, so the first 2 matrices were easy. The 2 composition, graphically, just one after the other, or one on top of the other. Okay, so now let's look at the 2 other generators. So the matrix 1, 1 in both directions. So first, this matrix 1, 1. So if you take a vector x, y, then of course the result will be x plus y, which means this matrix is essentially the addition. Okay, it takes two inputs and one output, which is the sum of the two inputs. Okay, what I'm interested in is not just generators, but also relations. So let's think a bit about what are the relations that this satisfy. And of course, you know what addition satisfies. It satisfies associativity, which you can write this way. So if you have three elements, x, y, z, the order in which you do x plus y plus z is not important. And it satisfies commutativity. Okay, which says that the order in which the wires come to the node are not important because addition is commutative. Something else that I want to say is that as it is associative, we will use some notation. So what is at the right is the notation. It's just a notation to say that I'm doing the addition on three elements. But theoretically, just what is written on the left in a concise way. Okay, that is 1, 1 in this direction. And what is 1, and what is 1, 1 in the other direction? When, if you think a bit, you take x and you obtain x, x. So this is essentially a copy operation. You take one wire and you obtain two copies of the information on two different wires. So this is what I will write this way with a red wire. So you take one x and you obtain two x at the end. You copied the result. And what are the axioms that this red node satisfy? Well, if you think a bit, they are exactly the same as for the plus operation, but you write them in the other way. So for instance, if you want to copy something 3 times, the order in which you do the copy is not important. So you also have associativity. So technically it's called co-associativity of these operators. And you have also co-commutativity, which means that you can swap the wires. Once you have copied something, you can swap them, it doesn't change anything. Okay, so now we have understood what are the two generators, the blue generator, the red generator. So one of them is doing the sum, the other is doing a copy. And now we can go back to this and see that this is actually quite easy to understand. So I take this, and I use the picture, and this is exactly the same. So I replace every plus by a composition, spatial composition, every multiplication by a sequential composition, every generator by its picture, and I obtain this thing, which is a bit easier to understand. And to understand it completely, you see that I have a red node which goes to a red node. So red is copy. So I'm copying something and then I'm copying again. I will just put one node with 3 outputs, saying I copy it 3 times. And I obtain this. And now this is completely understandable. Why is it the matrix 1, 3, 2, 0? Well, if you look at the first coordinate of the vector that you want to multiply with this matrix, you have to use 3 copies of it. 1 copy of it will go to the top, 2 copies of it will go to the bottom. Okay, because you have the vector 1, 2 in the first entry. So this is why you have this red wire here. So, and you see that the input will be divided 3 times. 1 of them will go to the top, and 2 of them will go to the bottom. So this is how you do the 1, 2. And for the second component of vector y, you just have to copy it 3 times and use it on the top. So that's, here you see you use it 3 times. They go to the top, and then you do the addition of everything. So that's how you can represent matrices graphically. And now the question you can ask is that, okay, is that complete? Did I give all the rules for you to be able to represent matrices, to be able to prove things about matrices? And the answer is mostly yes. There is one rule that is missing. There is one rule that is missing. The rule that is missing is the rule that is saying that if you want to add, let's say, okay, if I want to add 2 numbers and then copy them, copy the result, there is another way to do that, is that I first copy the 2 numbers and then do 2 additions. So that's what you obtain there, and that's the last rule that you want. So a way to represent matrices graphically is by using essentially two generators, a blue one that is doing the addition, a red one that is doing the copying. So they should satisfy some axioms. So essentially, they should be associative, commutative. And they should satisfy this, which essentially says that if you want to add, then copy, then you can first copy, then add. Yes, Ville?
So two things. First, should I understand that in the slide where you told us that all the matrices come from these finitely many, you were proving that this is somehow a finitely generated category, and now you are telling, or maybe a monoidal category, and now you are telling us that it's somehow a finitely presented category?
Yeah, so
up to monoidal.
Yeah, so that's the slide that I wanted to go next, or previously.
Just a second thing. The 0 by 0 matrices which you promised to hide, are they hidden in the fact that you could also have something where you start a wire from nothing?
Yeah, essentially, you need them if you want to have rows of zeros or columns of zeros. And inside, if you look at this formalism, it means that your blue symbol, which is the addition, is not only a semigroup, it should be a monoid. And same for the red one, which will be a comonoid. But yeah, for the first one, yeah, so this is something which is quite nice, but probably that you haven't seen because these are not groups that I'm generating. And I have composition laws, I have generators relation, but that's not the usual generators and relations that you see usually. These are things that are very specific to a lot of work that is done in categorical quantum mechanics, and which is called a prop in the sense of category theory. So I will not give the definition of a prop, but a prop is essentially something which has these two laws. These two composition laws, spatial composition, sequential composition. So that's essentially what a prop is. And what you have there is essentially a presentation of the prop of matrices. The prop of positive, non-negative matrices. Okay, there is nothing to the minus there. I am just doing non-negative matrices, which is exactly what I want. I don't want negative numbers due to the initial problem. So this is nice because this is a way to do reasoning about matrices entirely with pictures. So everything I can do with matrices, I can do the same using pictures that represent the matrices, and the composition law, everything works quite well. So this part is not new. This is something that is quite of folklore that you can see in nice articles by Fabio Zanazzi in particular. And what is new is what I will build on top of it to do what we are interested in, which is strong shift equivalence. But the first part of the talk, which I think is quite nice, is that there is a way to represent matrices with pictures. And now that we have this way to represent matrices with pictures, we can use them to reason and to say things about equivalence. Another thing I want to say is that matrices are not the only thing that satisfy all these axioms. There are a lot of other structures that satisfy all these axioms, which is very important because as this is exactly matrices, it means that every other model, there is a morphism from matrix to any other model that satisfies this, essentially by the universal property. So, for instance, instead of having addition, I can have addition of integers, I can have any other kind of addition, any other kind of monoid. This will still work. This gives a way to see a morphism from matrices to some other objects, for instance. We will see that at the end. Okay, so that's good, but that's not what I want to do. What I want to do is to investigate conjugacy. And investigating conjugacy is that I want to take this equation and I want to somehow quotient by saying that Rs is equal to Sr, because that's what SSE is saying. But there is a problem with that I cannot say that a 2 by 2 matrix is equivalent to a 3 by 3 matrix. Because if I have a 2 by 2 matrix in some diagram and I try to replace it by a 3 by 3 matrix, I don't know what to do with the additional wire. It doesn't work. So I cannot do it quite directly. That's what I'm saying. Here, there is something to do. But actually, there is an easy solution. There is an easy solution to that, but you cannot just say, OK, I look at all generators and that says that AB is equal to BA. It doesn't work because they don't have the same type. You cannot use them at the same place. So I will use something else, which computer scientists like to do, which is to add loops. And that's what I will do. Now I will add something new to the language, which is the possibility to have loops. So loops is something that take an input, an output to an input. Okay. So now my diagrams are different. Before they were representing matrices. Now I do not know what they are representing, but they are exactly the same diagram, except now I am allowing loops to loop an output to an input. Okay, so it's slightly different model. We have something new in the language, which is called a trace in category theory, which is just these loops. And what are the axioms that you want of these loops? So actually, there are two of them that are quite natural. So the first ingredient is that if you do GF, then of course, due to the fact that you have a loop, you can put the G anywhere you like, it will still be the same computation. You are essentially just pulling the G from the right to the left, and you have the loops to do that, so it should be possible. So that's one of the axioms you want. And the other axiom you want is that if I do a loop like that, then I have done nothing, essentially. So if I take the permutation of wires and I loop just the first wire, then I'm doing absolutely nothing. So that's the two rules I have on loops. Essentially, that when I have a loop, I can translate one of the boxes from one part to the other, one part of the loop to the other, and the other that if I do just a small loop like this, is the identity. Okay? So the thing is that I didn't invent those rules. Traces exist, and just that they exactly correspond to what I want. So that's perfect. I'm not inventing some new concept in category theory, I'm just using things that exist and that actually appear in the literature. So that's good. That's a good foundation for what I want. Okay, so now I'm just saying, okay, let's look at this collection of generators and relations. When I have one additional thing, it's not really a generator or relation, which is the fact that I can do loops. So in particular, of course, NM and MM, if I do loops, are the same. That's exactly what I want. So now if I want to prove that, if I want to say that M and N are SFT equivalent, so that they represent conjugate SFTs, I just have to put loops around all the wires, all the inputs, and I'm done. So this is the theorem we obtain. So I forgot to put the star in the theorem, you will see why. If I have two matrices M and N, then I can know if they are equivalent by just putting wires like this, putting loops like that, and looking if now I can prove that they are equal, using all the equations I gave before. So that's quite nice. And what is also quite nice is that if I cheat a bit with the pictures I do, I obtain something nice. So for instance, if I look at the 2x2 matrix on the left, so graphically it corresponds to what is on the center. So you have these three things that correspond to the three inputs and the three input things that correspond to the output. And I put the loops to say that I'm doing the loop. Well, if you kind of take together, merge together the red and the blue part of the loop, you obtain what is on the right, which is exactly the graph that we started from. So the difference is that now the graph is representing something. It's not just a graph. It's actually something that has sense for the construction I'm doing. So that's quite nice. There is just one small problem, that it's not a theorem. Okay, so it's not a theorem because there is I use exactly as I said the definition from category theory, and the last one actually we don't want it. And I have to use it because otherwise I have something which is a very strange object, but we don't want it because if you have it, then 0, 1, 1, 0, and 1 are conjugate, are SFT. Why? Because essentially 0, 1, 1, 0 is the matrix here. You see that the red and blue node do nothing, so it's essentially two loops, or one big loop, and as one big loop is equivalent to no loop, so this is equivalent to this, which is equivalent to this. So now, for everything I have done, the matrix 1, 0, 0, 1, 1, 0, and the matrix 1 can be proven to be equivalent when I use loops, which is bad. That's not what I want. But actually, if I think a bit, I say, oh, but this reminds me of something I've seen when I've read articles about equivalence, that there are other notions of equivalence for matrices. And actually, what I obtain is not strong sheet equivalence, it's flow equivalence, which is another notion of equivalence of matrices, which is quite well known. And so there is a problem with what I do, is that essentially, if I have two loops, I cannot see the difference with just one loop. And so this theorem, actually, you can find it in an article by a physician, a physicist, about quantum fields. So there is a thesis by David Hillman, which speaks only about quantum fields, but right at the middle, there is something about flow equivalence and matrices, because he found this investigating quantum fields. But from our point of view, it's bad. And the reason it's bad is that when you do 2 times a loop, it's not the same as if you do once the loop. So it means that the representation has lost a notion of time. Essentially, that the fact that I take a wire is not consuming any unit of time, and that's a problem. So what I will do is that I will add a notion of time. So what is a notion of time? It's just something that needs to be there, that cannot disappear, but when you do the unit of time is not important. So essentially, it's just a morphism. So the morphism will be represented by the square, the yellow square, and the only important thing about the yellow square is that it's there. But you don't need to be there at some point, you just need to be there. So for instance, if it's there after the blue node or before the blue node, it's the same. It just needs to be there to mark that there is a unit of time. And same for the red node, it just has to mark that there is a unit of time, but you just can do it before or after the red node. You don't care. So, which means that now, when you are doing the loop, before doing the loop, we say, okay, and this should take 1 unit of time. So we add this square rectangle to say that it takes 1 unit of time. And now there is a theorem. Now you can prove that 2 matrices are equivalent if and only if you can go from one of the matrix to the other using the equations. So we now have a way to, with generators and relations, to characterize exactly conjugacy. So for the proof of that, the main idea is that once you add this square, somehow you are not representing matrices with integer coefficients, but with polynomials. When you see t as representing 1 unit of time, and then you have to use results from Boyle and Wagoner to obtain the fact that it's exactly what we want. But essentially, we have a way to do that, so to take 2 matrices and to prove that they are equal using the equation. How much time do I have left? Okay. So let's try. I want to prove something very easy, that the matrix 2 is equivalent to the matrix that is there. So I will start with the matrix 2 that I put as a picture. So what is the matrix 2? You take the input, you have to copy it, and then sum the 2 copies. Okay, so that's what you obtain there. And then I add the loop, and at some point on the loop I put the square. Where the square is not important. Okay, and now I want to change things to obtain some other matrices. So the first thing I will do is say that the square is not at the good position. So I will put it there. And then I say, okay, I don't really care about where the symbols are because I have loops everywhere. I will reorder the things so that the blue node is before the red node. Okay, by just pushing the red node there. Okay, and now what do you see? You see that you have a red node, a blue node, which is again addition, and then you have a red node, which is copy. So instead of doing the copy, the addition and then the copy, I can do the copy first and then the addition, which is that. Okay. If you look at what you obtain there, it's the matrix 1, 1, 1, 1. So in our picture, we are going from the matrix 2 to the matrix 1, 1, 1, 1, which is this matrix. Okay, and then I want to make it a bit more complicated. So this one is, of course, I know what I want to do. So the transformation I will do exactly the transformation I need for the proof. What I need is to slightly change the position of the square on the top, but not on the bottom. There is no real explanation for that. Just I know because I know what is the result. And then I will do the same as before. I will put the blue points before, and you see at the top, you have again the same picture. You have an addition and then a copy. You can do the copy first, and then the addition. You obtain this thing. And here is a quite tricky part. You have to add. Okay, so just it's not tricky. Just I'm putting it like this to see. Okay, now you see that I have two red symbols. Two red nodes, which means that I am copying something and then copying again. I will transform that into 3 copies. And another thing that appears that I'm not really happy about the 2 blue points without a red point on it. I will put a red point in the middle. So this happened here. That's the first operation. That's the second one. And then I reorder everything and obtain this. And this is exactly the matrix that I want. Okay, so there are 2 things that you should understand from what I just did. First, that it's possible. Second, that it's a lot of steps. Why is it a lot of steps? Is because if you think about what we did, essentially we are very low level. It's essentially the assembly language version of the SSE problem. So of course, every step is now decomposed into many, many different steps. And that's why it takes a lot of time to do that. So in the next slide, when I will explain what this gives us, it doesn't give us simpler proofs that some things are equivalent. No, the proofs will be longer. So what is the main application? So there are a few applications of that. So the first application is that, okay, if someone is capable of saying to me what is exactly the object that is representing by all these generators and all these relations, then we have one. Okay, of course. But I don't expect anyone to say it. Let's verify. Okay. The second one is that if we look at what we did, it's possible to obtain a definition of conjugacy which is compositional, which means that you can take small graphs and say something about what happens if you put them together and use conjugacy on the small graphs to prove something about conjugacy on the bigger graphs, which is quite nice. And what I will be interested in the remaining part of the talk is how to use that to find invariants. And what is the idea? So the idea is that let's forget about matrices. We have a set of equations, we have a set of generators. Let's try to find structures in the wild that satisfies all these equations. And there will be some. I promise you there are some structures other than matrices that satisfies all these equations. So let's try to find structures in the wild that satisfies all these equations. If you find one, what do you have? Well, you know that the matrices satisfies all the axioms and no additional ones. You know that the structure you find in the wild also satisfies the equation, but might satisfy more equations. So what it means is that actually there is a morphism from matrices to your structures. Okay? Well, technically it's a functor, not a morphism, but from the structure to your new structure, which means that you have now a way to find invariants. Because now you take your object, you take your matrix, and instead of interpreting the matrix in the realm of matrix, you interpret it into your new structure, which might have objects that are very different from matrices. And what you obtain is, by construction, something which is invariant, which is an invariant of conjugacy. So there is a way to obtain invariant of conjugacy by just looking at structures that satisfies all the axioms and transfer matrices inside them. So here are just the axioms so that we don't forget. So these are the axioms that we want. And what is very nice is that there are examples in the literature that already exist of that. So there are a lot of such structures in the wild. And that's very good, because it means that instead of having to think about how to find invariants, I just have to do bibliography. So that's a different way to find invariants. Instead of thinking, I just do bibliography to find structures that satisfy all these axioms. And actually, so they exist in literature, but there are quite a few differences. The main difference is that usually they satisfy either less axioms or more axioms, and so you have to tweak them so that they satisfy exactly what you want them to satisfy. So for instance, there is an object which is quite well known in algebra, which are Hopf algebras. Hopf algebra satisfies all the axioms that I'm saying plus one more, because Hopf algebras, they correspond to negative, positive or negative matrices. There is something to say -1 in Hopf algebras, and I don't want -1. For SSE, I don't want -1. So it means that if someone says, hey, I have an example of a Hopf algebra, maybe you can use it to obtain an invariant. You say, okay, but I have to somehow force it to remove this way to do the -1 because I don't want it. There is another problem, is that most of them do not have loops. So I need to find a way to add loops. And what is quite interesting is that for some examples, the way to add loops will actually remove the Hopf algebra. So I can adding the loops will remove the -1 in some occasions. So I have a way to do that. And so to prove that this approach is successful, now I should give example and prove to you that the examples are similar to things that we did already in symbolic dynamics. So I will give 3 or 4 examples. So the first one, I said it before. What is the easiest structure you can think of when you have something that gather and something that do the copy? Well, instead of doing it over the integers, you do it over any monoid. So that's the first example. So you take a commutative monoid. The addition, which I call product, is just the addition. The coproduct is just the copy. And there is this problem with the trace, because it's not clear what it means to take the output back into the input. Intuitively, it's a fixed point. So the row about trace is fixed point. There is a lot of quotes in this row. But if you do that, you obtain this thing, which I don't know if it's known. It's not hard, but I don't know if it was clear that it is an invariant of conjugacy, which is if you have a commutative monoid and a morphism for this commutative monoid, then if you look at your matrix A, essentially at the solution of H of AX is equal to X, then the number of solutions of such a system is an invariant of conjugacy for any monoid you can take. So, for instance, the easy case, if you take H to be the morphism over the complex numbers thing as an additive monoid, which is just multiplication by lambda, it means that the existence of lambda being an eigenvalue is an invariant. Okay? So it's not mx is equal to lambda x, it's lambda mx is equal to x, which is why it doesn't say nothing for lambda equals 0, because lambda is not at the good position. So this is something that we obtain, which is quite interesting. That okay, if you take any commutative monoid, any morphism, the number of solutions of this equation is an invariant of conjugacy. I don't know if it's known, if it can be used for something, but it's quite obvious from the point of view I took. The second example, which I think is more interesting, is that you probably, most of you have a team in your building that is doing combinatorics. And if you speak with them, and you speak with them of Hopf algebras, they will say, okay, there is a very classical example, it's the symmetric algebra or the polynomial algebra. And what does it do for us? So this is the example. So this is an example of, now what we have is that the maps takes polynomials as input and give polynomials as outputs. And essentially you have as many variables in your polynomial as wires in your as inputs. So what is the product? So you take let's say a polynomial with x as an unknown and the polynomial as y as an unknown. Well, the product is just you merge the two unknowns in one. And the other direction, you do the opposite. So you replace x by y plus z, y1 plus y2 in the slide. And so this is a very well-known example. And it kind of works. It's usually not only a B-algebra, but a Hopf algebra. It kind of works, and now you say, okay, that's great. So there is no notion of trace, so you have to think a bit about how to do the trace. And to do the trace, I'm forced to completely change what they are doing and replace polynomials by formal series and fields by semi-fields, semi-rings, but it works. So if I replace it by a semi-ring, I obtain something very interesting, is that I obtain directly the data function as an invariant. I don't know why, I didn't expect to obtain it. I just say, okay, this is very well known. Let's try to look at what I obtain, and what I obtain is exactly the zeta function, which is quite nice, which shows that the method is not stupid. I obtain something interesting by using this method of looking in the literature for Hopf algebras and trying to see what I obtain as invariant. Okay, and the last example is a bit more conceptual, because now I cannot see the object as acting on anything. So I see my object as having some input wires, some output wires, but first, there will be no difference between input and output, I don't care. And my object will represent groups, and the input and output wires is just point in the group that are marked. And putting two groups together means that I have to identify the points that I'm putting together. Okay, so this is very strange, but actually it makes a lot of sense from a point of view of category theory. So my pictures now represent words. Putting two groups together means I have to quotient over the elements that I have identified. And if I do this, there is a clear way to do product, to do sum, which is I take the group that has three generators, and the third one is the sum of the two first. So of course, this is Z2. The group is just Z2. But I take Z2 as a group which has two input generators, one output generators. I say it should be the addition. I take the copy to be the group that say I have three marked points, but they are all the same, which is exactly the group Z, another way of presenting the group Z. And if I do that, it turns out that what I am associating to something is exactly the Bowen-Franks group. So the Bowen-Franks group can be obtained in this way by looking at what happened for this very strange prop where objects are not matrices but are groups. And if I do this with something else than groups, so for instance with semi-modules, so if I take ZT's modules, is that exactly the same? So now my objects are not groups, they are ZT modules. When I put them together, I have to quotient by what is put together. Then what I obtain is exactly the dimension group. So it works quite well, and we see that most classical invariants, not all of them, many classical invariants, you can obtain using this approach. So what is bad is that I did not find a new one, but I found many of the existing ones. Okay, so that's it for the idea of this talk. So essentially, what I obtained is a new way to construct invariants by just finding in the literature, or inventing, but mostly finding in the literature examples of algebras, tweaking them a bit, and then I obtain immediately an invariant using that. So this approach is quite successful because I obtain some invariants that are well known, which means, okay, I don't obtain just stupid invariants, but all the invariants we know. And of course, the next step is to find new invariants and of course to find a total one. Okay, thank you.
Are there any questions? Ville.
So first, joke, comment. So this talk is kind of contrarian because you multiply from the left. Why don't you multiply from the right? Okay. Next thing. Sorry to be dense, but what are the invariants that you don't get? Because these are the three that I could think of.
So if you think at what I obtain as a particular property, that if I take m and n, then and I yeah. So my morphism phi has a property that phi of m in parallel with n will be phi of m in parallel with phi of n, which means that all my invariants have this property. That if I take two disjoint systems, the invariant of the union should be a combination of the invariants of the individual systems.
Ah, but you were actually advertising this as a positive thing, or somehow on one of the slides. But yeah, okay. Secretly, it's actually a bad thing. Okay, I'm sorry. Okay, joking.
You said that if we had a concrete representation, I think that's the word you used, of this structure, then we decide conjugacy. I'm not sure what you mean exactly. Would you mind explaining a bit more?
So essentially, if someone can be said, okay, this is just a matrix with, okay, if I say, okay, these objects can be thought as, let's say, objects in some coded by words, and I have a relation to say when two of them are equivalent with computability assumptions, then I decided conjugacy, essentially. So now my object started concrete, it was matrices, and adding the wires made them not as concrete anymore, because now I have some equivalence that appeared due to the fact that I add wires. And so I need to find some other way to describe them, possibly, to find yeah.
Okay, but so finding the representation, so finding the representation doesn't magically solve the thing. You still have to solve the problem is a new representation.
I mean,
right?
when I say representation is in the idea of something that is understood.
Okay, I see what you mean.
Two questions. The first is, I understand that as some kind of rewriting system, that you have a drawing and you can rewrite things. Does it have some nice properties, or is it completely lost? Like, okay, maybe confluence and termination are too big to ask, but can you ask for something?
I mean, if you can answer this question, you can answer conjugacy, essentially.
Yeah, I understand that.
So, as I said, for the case of one-sided shifts, the rewriting system you would obtain has fewer rules, and now it's confluent, which means anything is easy. For this one, yeah, essentially trying to find any property of this system is probably the same as solving conjugacy.
Okay. Second question is, I didn't know about that before. Can you give an intuition about why SSE is equivalent to these matrix rewriting, like equivalence relation or not?
Which part?
So, why SSE is equivalent, in fact, to conjugacy?
To conjugacy?
Yeah. If it's too complicated,
it's
then
a
forget
bit complicated, yeah.
Okay, forget it. Thanks.
So I have also two questions. The first one, can you use your method to prove that very simple examples are conjugate? For instance, there are 2 by 2 matrices where I think it's open.
Yeah. So of course, I tried a lot of time to look at 1, 3, 4, 1 and 1, 12, 1, 1.
Yeah.
It's not clear. So again, as I said, we are really at the assembly language level, which means that the proofs are much more complicated if we want to prove that things are conjugate. It was better to find invariants. So I had some ideas on how to use, I don't know where I am in the slides. For instance, to use this thing, which is very elementary, but I don't know if everyone knows about it, to try to separate these matrices, but I didn't find a way to do that.
The second question is, do you have also a model for the one-sided case, which is much simpler?
Yeah, it's much simpler in terms of our understanding, but in terms of doing it algebraically, it's not that simple.
It's not that simple.
You cannot. I do not know if it corresponds to something for matrices, so I don't know.
Okay, if there are no other questions, please thank Emmanuel again.